everyone. Very good evening and welcome back to GFG Practice. So, guys, today we'll be discussing yesterday's problem of the day, that is Kth Ancestor in a tree. Hi, Rishit, and hi, everyone else as well. So, guys, please give me a +1 in the chat and hit the like button if everything is working fine. And then I will share my screen so that we can discuss the problem of the day. That was Kth Ancestor in a tree. Okay, I hope that everything is working fine for us. So I'm sharing my screen now, and let me know once it's visible. All right, hi Mau as well. So yeah, let us start off with this problem and let's see. Binary lifting, actually, Utkarsh, the thing is, I also thought about binary lifting, but the tree is not given in the adjacency list format now. So that is why binary lifting will not be done here at least. Okay, so yeah, basically in this problem, we have to find the kth ancestor in the tree. So the problem says that you have been given a binary tree with n nodes and you have been given a particular node. And for that node, you have to find the kth ancestor. Okay, if the kth ancestor does not exist for that node, then return -1. So suppose if you have this particular tree, okay, so let us say that what you have is, if you have this particular tree, so you will be given the node, root node of the tree. Okay, so let's say you have been given one, then after that one you have two connected to it, then you have three connected here. Okay, then after that you have four and you have five. Okay, so like if I will ask you, let's say you are there. Okay, you are there, and if I'll ask you what is your first ancestor, so first ancestor is nothing but your father. Okay, your father, your itself. Then if I'll ask about you, what is your second ancestor, right? So second ancestor is nothing but your grandfather. Okay, grandfather. Then what is your third ancestor? If okay, so third ancestor is nothing but great grandfather, like that. So this is what they mean as the kth ancestor. So k is equal to 1 means that your first ancestor, that is your father, it's yourself. Okay, so suppose if we have been given the node and we have been given the node value as 4. Okay, so suppose we have been given the node value as 4. So for this particular node, we have to find that what is, for this particular node, what is the second ancestor. K is equal to 2. So basically one ancestor above, if you go, so this is the one ancestor above, and one more, like for this, if you go one ancestor above, so total you are traveling how much ancestors? Two ancestors. So for this guy, if you travel one ancestor up, so you'll go to the father, and for father again you go to one ancestor up, then you will get what? Then you will get the total two ancestors up, right? So that is nothing but the great like grandfather here. So basically for the answer is nothing but one here. Why it is one? Because two ancestors up, the node is one only. So is this sample example clear to everyone, guys? Please tell me in the chat. I'm just looking at the chat now. So is it clear to everybody till this point, guys? Please tell me. Okay. And hit the like button, guys, if you are clear till this point. Okay. Everyone is clear till now or not? Yeah, Rishit is clear. What about others? Okay, everyone is clear. Now, what I want to do is, now, if you will observe, what we did was, if you observe, right, if I have been given anything, suppose I have been given what? Suppose I had been given this particular tree. Let's say if I expand it further, okay. Let's say I'll expand it like this, something like this, okay. And let's say if I will name this as 7, then 6, then 8 and 9. Okay. Now, suppose that for this particular node, I wanted the fourth ancestor. Suppose for this node, I wanted k is equal to 4. 4 ancestors up I wanted. Okay. For this particular node 8, I wanted 4 ancestors up. So what will you do? Like for this, you will go one step up. Okay, to this one, right? Then from this current node, you will go to this like one ancestor up again. Then from here you will go one ancestor up again, right? Then from here you will go one ancestor up again. Okay, so total I think you can see 1 2 3 4. Yeah, so you can see 4 ancestors up is this total part, right? So overall from everybody, like from your like current, you go one ancestor up, one ancestor up. So 4 times when you go up, then you can see that like the ancestor is for 8 case, fourth ancestor is nothing but 1. Okay, is that clear to everyone, guys? So now the thing is that we are building an answer step by step. Okay, step by step. So the thing is that what do we want to store if we want to go up? So for a particular node, you want to store something, right? For every node, if you will observe, so for every node, what you need to do is store its parent. Okay, so basically for every node, store its parent. Now what do I mean by this? So when I say this thing, so let's erase this part from here. So for every node, what we should do is we should try and store its parent. Okay, for example, if we have this particular node as 4, suppose, Okay, then for 4, like we should have an array in which we should say that parent, like we can have a map or something, map or an array, and we can say that parent of 4 is what, 2. Okay, then we can say that parent of what, parent of 5 is also what, 2. So we should update for every node, we should know its parent. Okay, similarly for parent of 2 we will update it as 1, and for parent of 3 also we'll update it as nothing but 1 here. So that is why for every node you should know its parent. Is that clear to everyone, guys? So we need either an array or a map data structure in order to store the parent for each and every node. Is that clear to everyone, guys? Please tell me. Is this part clear? That for each node what we want is we want to store the parent, like for the parent of that node, because every time we want to go one step up, so we should go to its parent from the current node. If we want to go to one node up, so basically we should go to parent of the current node. Okay, that is one thing. Now in this case, if you will observe, guys, if you will observe, so what can we do? Like in a general scenario, what can you do? So if you will observe here now, suppose this is the root node. Okay, and suppose you are doing any kind of traversal, either it is in order, pre-order, or post-order. Let's say if it is pre-order traversal, so suppose you are at the current root. Okay, then if you are at this particular current root node now, so if the left child exists, so basically what you will do is you will simply say that parent of root dot left. Okay, parent of roots left is equal to the root. Okay, so in this you will update this, and basically if the right child also exists supposingly, then you will say that root dot right or root arrow right is equal to root. So basically right child's parent is this root. So basically if you are at this particular current root, if you are at this node, then for its children you will update their parent as this particular node 2. So for this node 2, if you have the child as 4 and left child as 4, so you'll say that parent of the left child is nothing but 2 itself. And again you will say if the right child exists, so parent of the right child is nothing but what, it is nothing but this particular guy, that is 2. So is that clear to everyone how we are updating the child and parent relationship using a map? Like we can use a map data structure here, kind of. Till this point everyone is clear? Please write yes or no. If you are clear, please hit the like button also, so that I can understand that till this point you are clear that how to store the parent for each and every node, na guys? Okay, I cannot see responses, so let me know. If there is any doubt till this point, you can let me know. Otherwise, all right, clear. Okay, so yeah, first thing is that we want to iterate through this particular given tree. Okay, and we want to store the parent. So basically what I will do is I'll declare an unordered map. Okay, so basically a hash map in Java. So you will declare a map. Let's say what you will store is with respect to every node, you need to store the like for every node you will store the parent. So this will be a node common node kind of thing. Okay, because for every node you are storing its parent now, so this will be a node common node relationship, and let's name it as parent array. Okay, parent. So yeah, now after this, let's say we will call the pre-order. So pre-order is what? I think pre-order is root, then left, and then right. Yeah, so let's call the pre-order traversal. Okay, you can call any of the traversals because we just want to traverse throughout. Okay, so what you can do here is now afterwards you can basically pass the root node here, and then we can pass the map, that is the parent map. Okay, then when we pass this, so the return type will be void. So we will write void pre-order. Let's say pre-order. So we are traversing this particular tree, and we will be at the current like let's say we'll be at the current root node. Okay, and I am also passing the unordered map. Okay, and I'll pass it with ampersand because any changes that I make to it should be reflected finally also. So ampersand map parent, let's say. Okay, so I'm passing this parent map, and then I'm passing this root also. Now what I will do is, if suppose that the root is equal to null, if the current root that I have reached, if it is null, then simply what you do is you just return from there. Otherwise what you will do is, firstly you will check that if the root's left child, okay, suppose for the current root, if the left child exists, if it is not equal to null, if the left child exists, then you will say that for the left child the current root is the parent. So parent of the let's update it, parent of the root left. Okay, so for the left child the parent is this particular root node itself. Okay, and similarly what we will do is we will check that if the roots right, if it is not equal to null, okay, then in such a case what you will do is you will say that parent of roots right. Okay, you are going to update it as the root. Is that clear to everyone, guys? Till this point, everyone is clear? Please tell me. Is this part clear to everyone? And then what you do is you so basically you process the root. Okay, for the root you process the data, and then you will call the pre-order traversal for the children of it, because you want to update for the children also. So you will call the pre-order traversal for the root's left child as well as the right child. So you will call the pre-order traversal for the root's left, and you will pass the parent map, and then again you will call the pre-order function here for the root's right child. Okay, and then you will pass the parent here as well. So is this much part clear to everyone, guys? Please let me know. Okay, yeah. So basically what we have done is, up till now we have stored the parent for each and every node. Okay, now what we will do is we will check whether the current node that we want to search for, okay, suppose they will give me, suppose this is the tree. Okay, so suppose if this is the tree that has been given to us, so let me just update this here. Okay, suppose this is the tree that has been given to me, and the k value has been given as what? Suppose the k value has been given as suppose 2, and we have been given the node as, let's say, 7. So for 7 I have to find the second ancestor. Okay, suppose, guys, for 7, for the node 7, for the node with the data as 7, I have to find its ancestor. So please tell me, does there exist any node 7 here at the first place? Please tell me, does there exist any node as 7? No, there does not exist any node as 7 itself. So that is why it is very important for us to check also whether it is existing or not. If it is existing, then what we will do is we'll point at that particular point. Otherwise, if that does not exist now, if the node for which we are looking for the ancestor, if that node itself does not exist, then we should directly return -1. Okay, so basically what we will do here is, just give me a second. So first thing is that we will iterate through the map. Okay, so just a second. Okay, so the first thing that we will do is we'll iterate through the map. So let's say for auto, like is to map. So basically we'll iterate through each key value pair of the map, and basically I dot first will tell me about all the nodes. So I will check that if there is any I dot first, okay, which is equal to the node itself. Then in that case, what I will do is, let's say I will have the value here. So let's say initially I can have let's say I can have node star current. Okay, initially I'll mark it as null, indicating that it is not present. Okay, now I dot first is there. So first of all, like if I find that particular node, okay, so if inside the map I'm searching, and if there is any node whose data is equal to the node that has been given to me, then in that case I'll say that, okay, I'll store that particular node. Okay, so I'll store that particular node from which I want to find, and then I'll simply break away from here. That is what I will do. Okay, and like you can simply check for security purpose that if the current is equal to null. Okay, if the current is null, so this will indicate that there does not exist any there does not exist the node that was given for which I had to find the ancestor. Then in that case you can return -1. Okay, otherwise also there will be chances when you have to. So like assuming that the node that has been given for which we have to find the ancestor, it might not exist, so we are just checking. If it exists, then it will be stored. Now suppose that you are searching for 4 here, guys. Okay, so let us move to this particular point now. Okay, suppose that you had been given the node as 4 here instead of 7. Suppose that node was given here as 4. Okay, so basically inside the map what happens is, inside the map like you have these things stored. Parent of 4 is stored, parent of 5 is stored. Okay, then you have what, parent of 2 is stored as 1, then you have also parent of 3 stored as 1. Okay, so then we look then we are looking at the keys. So basically I dot first is what? I dot first is this particular part, this particular part, all these nodes, right? All these nodes. So I'm checking if I dot first exists or not. So is there any I dot first which is having the value as 4? Yes. So we can say that this particular node is there. So in like what will happen, our current will stand at this particular point. Now how many times I did this same way recursively? Okay, so yeah, now what we need to do is, guys, now after this we have our current standing at this particular point. Okay, now how many times we need to run the loop? We need to run the loop k number of times. Okay, we need to run the loops how many times, guys? Understand how many times we want to go up and up. We need to go 2 times. Okay, because for this node we want to find the father. Okay, and then after that our current will move here, and then from this node we want to find what is the father. Then ultimately when we repeat this process 2 times, then we will get the ultimate father. Okay, so that is what the scenario is all about here. So basically what we will do is, suppose we are currently standing here at this point, right? So if you are standing at this point currently, so if you are standing currently at this point, right, at this particular point 4, so like k number of times we have to repeat the process. So I will say that while k is greater than 0, and since I have to repeat the process k number of times, so let's decrease the k. So k number of times I have to keep on moving up and up. So what I will check is, I will check that for this current guy, does there exist its parent or not? Like, tell me guys, for this guy 4, does its parent exist, yes or no? So basically I will check inside the map array. I will check that so initially, let's say I will obviously we have the current updated here now, yeah. So like for this guy I will check. So I will check if the parent dot find inside the parent array, I will parent map, I will find that whether the current guy is having any parent or not. If it is if suppose it is equal to parent dot end, so if it is not present, if the parent for the current node is not present, so in that case we will simply return -1. Now what does this mean? So suppose guys what happens is, if you are at 4, okay, then after that you are at, like, you have 2 and then you have 1 also. Suppose that you want to find what you want to find k, let's say you want to find what you want to find, let's say k is equal to 3. Okay, so currently you will be here. Okay, then if you will check that, does the parent of the current node exist? Yes. So this is the parent of the current node. Okay, so you will move your current to this particular node, so the current will move here. Now after that, from here you check, does the parent exist? Yes. So you'll move the current to the parent, and from here, like, so see, you have repeated k how many times? 1 time and 2 times. So now the k is left only 1, because one time you have gone up and another time you have gone up, but I wanted the third ancestor. So from here you check, does there exist any parent? So the answer is that there does not exist any other parent, right? So from here there does not exist a parent. So this means that for this current guy there is no parent. So this basically means that it does not have since it does not have any parent. When I check inside the map, so 1 does not have any parent. So this means I don't have a third ancestor or a fourth ancestor. Are you getting my point? If I have to search for a higher ancestor, so whenever I'm at a current node and its parent does not exist, so this will directly indicate that overall the current node, this initial starting node, did not have any kth ancestor. Is that clear, guys? Please tell me in the chat. Are you getting my point? See, what I'm saying is, suppose you had to find, suppose this was the tree given to you. Okay, suppose this was the tree given to you, and you had your current here. Okay, this was the node, and you had been given k is equal to 5. Suppose, so for this node you had to find the fifth ancestor. So you will go you will be at this, you will check if the current parent is existing or not. Yes, it exists. So now what you will do is, your current will move to this parent. So current will decrease by 1, so current will point to 4 now. Then after that, for this guy you check, its parent exists. Yes, it exists. So the current now moves here. Now for this guy you check, does its parent exist inside the map? No. For 1, there does not exist any parent. So since the k has not exhausted, and for the current node you don't have any parent, so this means for this particular starting node itself you don't have the kth ancestor. Is this part clear to everyone, guys? So that this is what I'm saying, that if for a particular parent you are trying to for a particular current node, if you are trying to find its parent and its parent is not present, so basically this means that the kth ancestor for the given node is not present. Then in that case you should return -1, since it is not present. Otherwise what we should do, guys, is otherwise what we should do, so see, otherwise what should be done, I'll explain it here, just a second. Okay, so otherwise, suppose that your current is standing here, guys. Okay, let us suppose that your current is initially standing here, guys. Now for this guy, you will check. Okay, you start from here and the k value is given as 2. Okay, so 2 times you have to iterate. Now what you will do is, from the current you check, does the parent exist? Yes. So basically this is the parent of the current node, right? So now you will move the current to this particular parent node. So current is equal to this parent of the current. So now the current moves at this particular point. Okay, so it, since one step is done, so k decreases by 1, so k moves to 1. Now after that, what happens is, from this current you check whether its parent exists or not. Yes, it exists. So basically now this is the parent of the current node. So now you will move your current to the parent of the current node. Okay, so now the current moves here. Now obviously the k decreases by 1 more, so k moves to 0, and the k gets exhausted. So 2 times I have iterated up, and wherever the current is standing, that will be my that I can say will be my kth ancestor, right? Because I have moved up k number of times. So from this node I have moved 2 times up. So basically from current started from here, and now the current is standing here. So wherever the current is standing, that is the kth ancestor here. Is that clear to everyone, guys? Please tell me. Okay, so basically k times we moved, 2 times we have moved. Okay, 1 time from here to here, then next time from here to here. So now the current is standing here and it is not null. So basically this is the kth ancestor. right? So that is why for 4, the second ancestor is nothing but 1. Okay, for 4, the second ancestor is what, guys? Second ancestor is nothing but 1 now. Yes or no? Please tell me. And hit the like button if you are clear till this point, guys. Is everyone clear till now or not? Please tell me. Okay, and hit the like button, guys, if you are clear till this point. So please, just a request that hit the like button if you're clear. Okay. All right. Now, otherwise, as I said, the current will move to the parent of the current because it needs to go up now. So it will go to its parent. So parent, like parent is what? Like this one, na? So basically the current will keep on moving upwards in that particular direction, one by one. And at the end of the while loop, since you have the current existing, but then in that case, whatever the current node its data you have to return. So basically when the current is standing at this node 1, so you will return its data, and that's how you will return the kth ancestor indirectly. Okay, because you are moving k times up. So now let us try and do one thing. Let's try and run this code first of all to see if it gets accepted or not, guys. Okay, so yeah, I should write my parent here. Sorry. Now let's try and run it. It works fine on the samples. Let's try and submit this code and see if it gets accepted or not. I hope it should get accepted. All right, so this code does get accepted. So is this question clear to everybody, guys? Is this code clear to everyone? Please let me know. Okay, is it clear to everybody till this point? Right, basically first of all what you do is there are two steps in this question, as I said, right? There are two steps. The number one step that you are applying here, the number one step is store the parent of every node. Store the parent of every node, okay, by traversing the tree, traversing the tree. This is the first thing. And in a map you can store it, let's say. Okay, after that the second step is that uh, check if the node for which you want to find the kth parent, does it exist or not. And if it exists, then move k times up, right? Move k times up. So basically this means that if for the current, if its parent exists, then always what you keep on doing is current is equal to parent of current. Okay, always keep on doing this and do it k number of times, and at the end you return the current data. Okay, if that exists. Otherwise, if at any point of time, if any of the ancestor does not exist, so directly return -1, because overall kth will not exist. One small doubt, someone mentioned binary lifting. Can we use it here? No, we cannot use binary lifting here. Somebody said, so basically binary lifting is a competitive programming concept. I think Mao must be remembering it. So like basically if you consider the current time complexity, so it will be order of n for storing the parent of every node, and then another order of n for finding the kth ancestor, right? So overall time complexity is coming out to be you can say order of n, because if the k value is given as n, if I have to find the nth ancestor, suppose the tree is a skewed tree, okay, then in that case I will take n traversals. So the time complexity in the worst case would be order of n. And if you consider the space complexity, so since we are storing, so it will be order of n space also, because we are using the hash map and recursion here. Hi, Ash the Conqueror. Okay, so yeah, this will be the point. And obviously, if you have to optimize this, right? So if you have to optimize this, so suppose that the tree was given in the adjacency format. Okay, if the tree was given in the adjacency list form. Okay, like when we make a tree using the adjacency list now in competitive programming in CP. So there what we can do is we can use the concept of binary lifting, and there we can find it using order of log n time. We can find the kth ancestor in logarithmic of n time. So that we can do here. Okay, like that we can do, but whenever the tree is given in adjacency list, so that in that case it is better, since here it is given in form of node. So like it is not that optimal, but yes, binary lifting, if you want, you could have tried to use here. But yeah, you need to know binary lifting basically. Okay, so is everyone clear with this solution, guys? Please tell me. I'll just quickly provide this code, and this has been asked in a lot of companies I have seen personally. Okay, so yeah, let me just share this code with everyone. Thanks a lot, Harsh Srivastav, and I will share this particular code here. All right. Okay. So is there any doubt, guys, or everything is clear? If everything is clear till this point, so please make sure to do one thing. Please hit the like button if you have understood till this point, and please give me a +1 in the chat. Also comment down understood if you have understood this. Okay. After the video is over, also you can comment down understood. Okay. I hope that you understood this clearly, and make sure to do the problem of the day every day. And I don't know what the tomorrow's problem of the day is, but let me just check. Uh, Okay, so tomorrow we are like today's problem of the day is heap sort, and obviously it's asked in a lot of companies. So tomorrow we'll be doing heap sorting. Last time we had done quick sort, now we have to do heap sort. So we will see how we have to do it. Okay. So yeah, thanks a lot, guys, for joining for today, and keep coding, guys. Keep solving the problem of the day. I'll see you tomorrow with heap sort. Till then, take care and keep coding. Be consistent. Thank you, everyone.